Hi everyone. So my talk is going to be on how astronomers use different techniques to measure the distance to various objects in the universe, including stars and galaxies. So this is going to be a really quick whistle-stop tour covering a few different methods, but it's not complete and it'll be very quick and very basic. So we'll get started. So firstly, quick introduction to me. Covered most of this. I'm Tom, an astrophysics master's by research student at the University of Bristol. If you're interested, a master's by research is basically a mini PhD where a research project is squashed into a single year rather than 3.5 to 4 years. And my research is focused on giant impacts and debris disks, which is basically if you grab two planets and smash them together, see what happens. Right. So first really important question is, why should we care? Why are distances important? And there are a couple of reasons. So basically, initially it gives us a kind of sense of scale and allows us to kind of order the objects in the universe. So as you might know, some ancient astronomers assume that all stars are at the same distance from the Earth, attached to a kind of celestial sphere all the way around. Now we know that's different, and the stars we observe in the night sky are actually a variety of distances from the sun. This gives us an idea that the sun is part of a collection of stars distributed through space, rather than having everything kind of around the sun. However, we also, in the night sky, as mentioned before, we observe these kind of fuzzy dots that aren't quite stars, and eventually we find out these are galaxies, and they're much, much further away than all the stars we can measure in the night sky. So again, this gives us an idea that stars are grouped together in galaxies, and those galaxies are huge distances apart. So it gives us an idea of the broad scale of the universe on a kind of basic level. The second reason why distance is important is the universe is really, really big, as you might know, and light is comparatively slow. So this means it takes years for light to travel between stars and galaxies. So when we observe and take images of the night sky, we're actually looking back in time as well as through space. So if you understand how far away an object is, you also understand how old it is. And if we look billions of light years out into the universe, we can actually see some of the very first galaxies. So hopefully I've kind of convinced you that distance measurement is quite important. The next step is actually doing it. So for most of human history, we've used our own body basically to measure distance. So you have kind of inches, hands, feet, paces, all that kind of stuff. And we call these methods standard rulers. It's basically comparing the distance you want to measure to a physical object in the world. So for quite a few years, the standard meter, was defined as a metal rod that was held in a room in Paris somewhere, and you could compare all your rulers to the metal rod. But obviously, using these standard ruler kind of methods has quite a few shortcomings when you're trying to be really precise. So we've developed other methods to measure distance, which involve the transit time of a signal. So say if you have a distance you want to measure and you get a laser beam and you fire it across that distance, and then you measure the time it takes to cross that distance. If you know really precisely the speed of that signal, so with a laser beam, we know the speed of light very precisely. You can times the time it takes to travel that distance by the speed, and you get the accurate measurement of the distance. It's a bit more difficult to apply these transit time methods to measuring astronomical distances because there's a few shortcomings. So instead, we use a combination of different techniques called the cosmic distance ladder. So the general idea of the cosmic distance ladder is that there's no one true method of measuring distance across the scale of the entire universe. Instead, we have to use different methods that work at different scales. The methods that work over smaller scales are generally used to calibrate the methods further up the ladder, but this will hopefully make a bit more sense when I dive into some of the specific methods. And generally, as you get further up the ladder, the measurements get more and more uncertain because the errors from the lower end of the ladder build up and kind of propagate through. So let's quickly run through some of the techniques. So this is kind of step 0 within the solar system, we can still rely on direct methods of distance measurement. So we can measure distance by bouncing signals like laser beams and radar off of planets and asteroids and measuring the transit time. A really cool example is the lunar laser ranging experiment, which basically the Apollo astronauts left basically a mirror on the surface, several mirrors on the surface of the moon, and astronomers can point a laser at that mirror and bounce the signal back off and measure the time very accurately. So again, these methods involve actively sending some kind of signal and measuring the time it takes to return. This is great within the solar system, but as you try to study objects further away, like nearby stars, you run into a couple of problems. So it takes a long time for a signal to reach nearby stars, years and years, even traveling at the speed of light. And also signals generally tend to get weaker with distance, so it becomes more and more difficult to detect the reflected signal. So what other methods have we got? Well, one very simple one, but really effective, is the parallax method. So this method is based on trigonometry and geometry, and it's a really simple effect you can actually see for yourself. So if you hold up, say, your finger or your thumb and close one eye, and then quickly switch to the other eye, back and forth, you should hopefully see whatever object you're holding out with your finger kind of moves back and forth slightly with respect to a more distant background. This is because your line of sight is changing. So this is the effect used by the brain to kind of roughly get an idea of distance when you use your two eyes. It can combine the line of sight images from both eyes. And the size of the movement of your finger depends on the distance between your eyes and how far away the object is from you. And if we know the distance between your eyes, you could technically kind of figure out how far away the object is. We can use the same principle as we see in this diagram to calculate the distance to a star. So you need to observe the star from at least two different lines of sight. But helpfully, with the orbit of the Earth, we can get these two measurements. So if you take an image of a star at two different points in the orbit, so say 6 months apart, the kind of distance between your eyes is the diameter of the Earth's orbit around the sun. So if you've picked a target star and marked some kind of background reference stars, which are going to move less, you can take an image at each viewpoint and then compare the images to see exactly how much the star, your target star, has moved. And then using a little bit of fairly simple trigonometry, you can work out the distance. So this method is great for nearby stars, but as we aim for greater and greater distances, the parallax movement becomes smaller and smaller and eventually too difficult to measure. The current limit for parallax measurements using some really advanced techniques is about 30,000 light years. This is a really huge distance, but it's only about a third the diameter of the Milky Way, and there's still plenty of stars and other galaxies and all kinds of things outside that range. So we need other methods to get a bit further. Next up, we have this general idea of a standard candle. So this method is, well, this group of methods is based on something called the inverse square law for light, which in really simple terms basically means if you move an object further away, like a sun or a light bulb or whatever, it gets fainter. If you think about it, the brightness of the sun that we measure on Earth is going to be a lot lower than if you're floating in space right up against the surface. So this is a really useful law, because if we can measure the brightness from Earth and we know the intrinsic brightness of an object, which we call luminosity, then we can work out the distance with a really simple calculation. Measuring the distance from Earth is fairly simple as long as you have fairly precise equipment. But the difficult part is working out that luminosity, that intrinsic brightness when you're right up against the object. So this is where standard candles come in. They're a class of object where we can work out the luminosity from other measurements, not just the light measurement. So let's take a look at a classic example. So these are Cepheid variables. They're a type of standard candle. These are stars whose brightness changes periodically, but in a really stable way. So this makes it possible to measure and quantify the exact period of the brightness variation as I've marked here on this diagram of brightness changing over time. So in 1912, Henrietta Leavitt catalogued the periods of several thousand of these variable stars in the Large and Small Magellanic Clouds. These are kind of dwarf galaxies which are fairly close to the Milky Way but outside it. And she noticed a very interesting relationship between the periods and the brightnesses, which I just show here. That's a little screen cap from the original paper. It's essentially that the brighter the star, the longer the period. And she reasoned that because all these stars were probably at a similar distance from Earth, this relationship applies to their luminosity as well, and would hold for all Cepheid variables. So this means if you just measure the period of the Cepheid, you can work out its luminosity. And if you can measure the apparent brightness, the brightness from Earth, and you get the luminosity from the period, you can work out its distance. So with this method, astronomers were able to determine the distance to the Large and Small Magellanic Clouds, which are outside the Milky Way. And they calibrated this method to make sure it worked by measuring the distance using the parallax method to Cepheid variables which are a bit closer and within the kind of range of the parallax method. Okay, moving on, we have a quite exciting example of a type 1 supernova. So you may have heard of supernova. There are these huge explosions involving stars that can occur in a few ways. In principle, supernova can make great standard candles because they're really bright. They're seen across the Milky Way and in other galaxies. And if you're looking across a large enough scale, they occur kind of reasonably often that they're useful. The problem is that there's quite a lot of variation in their luminosity. So the most well-known type of supernova is a type 2 or core collapse. And this occurs in massive stars at the end of their life when they're unable to sustain reactions in their core anymore, and they collapse in on themselves and rebound outwards in a huge explosion. A lesser known type of supernova is called a type 1a, which kind of, there's an artist's impression here of that kind of ongoing process. This is a supernova that occurs when a small star called a white dwarf slowly absorbs material from another star, and eventually it gains enough mass to trigger a runaway reaction in its core, which causes a supernova. Because of the physics going on in the white dwarf, they have a fairly strict physical limit on how much mass they can have, which means all of these type 1 supernovae occur at stars in very similar masses. So actually, when you measure the brightness or the luminosity of various type 1 supernovae over time, in the light curve you can see on here, you get the same shape or very, very similar shapes over and over again. So the general shape here we see is it kind of reaches a peak very quickly and then begins to fade off. And it implies that they could be used as a standard candle because there's this kind of repeatable pattern we can see. However, in the image on the far left, you can see there's one slight problem, that they don't all quite reach the same peak luminosity. But luckily, the difference in peak luminosity is related to the rate at which the luminosity falls off after the peak. So this can be easily measured. And as you can see in the image in the middle, they've just corrected this. And so they all reach very closely the same kind of peak luminosity, which is great. So now we have an idea of a standard candle where we know what the peak luminosity is going to be, and we can just measure the peak brightness using a telescope, and then using our inverse square law, we find the distance. Final couple I'm going to look at are to do with galaxy relations. So these two relations are basically describe how the relationship between the characteristics of a galaxy and their brightness. So the first one on the left here is the Tully-Fisher relation, which is valid for spiral galaxies. So spiral galaxies are a family of galaxies with similar characteristics, including a relatively flat disk and kind of spiral arms, although there's a lot of variety within that. And classic examples are the Milky Way, the galaxy we live in, and Andromeda. So in very simple terms, the Tully-Fisher relation basically says that the rotation speed of spiral galaxy, how fast it kind of spins around, is proportional to its luminosity. So the faster a galaxy spins, the brighter it will be. And if you can measure the rotation speed of a galaxy, you can predict its luminosity. So once you've got the luminosity, you can measure the apparent brightness and work out the distance, same as any other standard candle. The Faber-Jackson relation on the right here is very similar to the Tully-Fisher relation, but it applies to a different type of galaxy called ellipticals. So these look a bit different. They're kind of smooth, a bit more featureless. And you can kind of think of the stars in an elliptical galaxy as like a gas. That's like gas particles kind of running around, flying around in the middle, with stars kind of whizzing around. You can actually measure the velocities of all these stars and measure something called the velocity dispersion, which is basically kind of the spread of different velocities in the galaxy. And again, this velocity dispersion is proportional to the luminosity of the galaxy. And again, with the standard candle approach, you can use this luminosity and measure the brightness and then calculate the distance. Finally, just a really brief mention on this. This is a fairly new method of standard sirens, which is, you may have heard in the news in the last few years about gravitational waves. These are ripples in the fabric of space, which are really tiny, very difficult to measure from Earth, but we've just managed to get the kind of precision and the technology to do this. And there's been an idea that the intensity of these gravitational waves kind of falls off with distance in a similar way to light. And we can use general relativity to calculate the original kind of intensity of these gravitational waves. We can measure the intensity at Earth and get an idea of the distance to these objects well, the source of these gravitational waves, which is generally to neutron stars or black holes or some kind of collision in space. But as I said, this is fairly new, and but it's really interesting because it could be completely independent of any other methods on the cosmic distance ladder. And so I think that's just about running over time. Yes, as I said, there's so many methods for distance measurement. This was just a really quick overview. And the distance ladder is the combined efforts of hundreds of astronomers across centuries. So it's a really great testament to the wide range of things going on in astronomy. So yeah, thank you for listening. And I'll try my best to answer any questions. Thank you.
How do you measure the rotation speed of galaxies?
Okay, yeah. So yeah, in spiral galaxies, generally you use the Doppler effect. So this was mentioned in a couple of the other talks. So generally, if a star in a galaxy is moving away from you or towards you, or some component of its velocity is moving kind of radially away from you or towards you, it changes the wavelengths of light you receive. And we can use knowledge of what the stars are to see how much that kind of shift is going on, and that's related specifically to their to their velocity. Sorry. So if you look at a lot of different stars within a galaxy, you can get an idea of the rotation curve, which is how the velocity changes as you move out from the center, kind of outwards. So it's a lot of Doppler measurements across all the stars in a galaxy.
Gosh, thank you. So my question was also about the Tully-Fisher. It was like, why is a galaxy more luminous if it's moving faster? Do you know?
So generally, I think it's related because the luminosity of a galaxy is kind of related to its mass. So the more massive, the kind of combined mass of the galaxy is going to be more luminous in like a simple way, because there's going to be more stars in there, so there's going to be more mass. And the velocity is related to the amount of mass in a galaxy. So it's kind of a few chain steps there. So generally, the more massive galaxies, there's going to be an overall greater rotation speed.
Okay, that makes sense. Thank you.